So in this video, I'm going to introduce the concept that we're going to be working on for the last section of the course, which is high-level state machines. As you can imagine, this is going to build off the finite state machines that we've already seen in previous sections of this course. So what I'd like to do in this video is first introduce a high-level state machine, show you what a high-level state machine looks like and how it works, and then at the end of the video, we'll spend some time talking about the differences between high-level state machines and the finite state machines that we've already been working with. So here is an example of a high-level state machine. Well, let's walk through and see how this works. I'm going to ignore this start one state for now. We're going to come back to that in just a second. We're going to pretend like it's not here for the time being. So the way that this works is we're going to start in the reset state, right? And then we will transition to previous 0 based on the fact that our input, dn is the name of our input, right? We're going to transfer to previous 0 based on the fact that dn is equal to 0. And then once we make it to this state, you can see that dn can be 1, that'll take us to previous 1. And then if dn goes back to 0, we go to previous 0. And so basically, we're just going to bounce back and forth between previous 0 and previous 1. That's how the inputs work. That's how the transitions work. Now let's take a look at the outputs. And I hesitate to call them outputs. You can see that this is a Mealy machine because the outputs themselves take place on the transitions, not based on the states. But the outputs aren't actually outputs. If you look at this output here, this says that when we transition from reset to previous 0, what we're going to do is take something called count and set it to a value n. So already we have something that's pretty different from the finite state machines that we're used to working with so far. Count is a variable, right? N is also a variable. So we haven't seen variables in our finite state machines before. That is something new. And we're also doing a variable assignment here. So we're not actually setting an output necessarily. Count is not our output of this finite state machine. It is not an output, right? But it still is important that we set count to be this particular value called n. So this quote-unquote output, this action, as I like to call it, in a high-level state machine, is going to set this variable count to this value called n as we transition from reset to previous 0. Right? So this transition from previous 0 to previous 1, you can see doesn't do much of anything. But when we go back from previous 1 to previous 0, you notice that this action down here includes an if statement. That's something that we haven't seen in our finite state machines before either. So we're saying if count is not equal to 0, there's a logical operator. That's another new construct to our finite state machines. So if count is not equal to 0, then I want to take a count and I want to set it to count minus 1. So I want to subtract 1 from my counter in this particular case. Right? So what is the output then? What is the actual output of this finite state machine? Well, that's given down here at the very bottom. Our output is called event. It's a single bit signal. Event is going to be true if count is 0. Otherwise, event is going to be 0. So what is this circuit actually doing? Well, we start in the reset state. We read in some value n. N is actually an input from the outside world. We read in some value n, and we set our counter to be that value. And then we start counting. If dn goes up and then goes back down, that counts as one thing that has happened. So we decrease our counter. So if n is 3, for example, right? dn goes up, and then dn goes down, our counter will now be at 2. Then dn goes up, dn goes down, our counter will now be at 1. And then finally dn goes up, dn goes down, and our counter will be at 0, which means that our event, our output, will now be true in this particular case. So what this high-level state machine allows us to do is use variables, use more complex structures like if statements, inequalities, variable assignments, even arithmetic operations. Here is a subtraction, right? Count is equal to count minus 1. That's an arithmetic operation. So we now have all of those tools available to us in our finite state machines as actions that we can perform in our high-level state machines. So let's go back and take a look at this start one state again really quickly just to kind of wrap this slide up. You can see that dn can be either 0 or 1. So the question is when we reset, right? what happens if dn is high already? Does that count as a single pulse or not? Does that count as a one of our counted items or not? And the way that this finite state machine is structured, it does not actually count. You can see that I move to this start one state if dn is high, and then I wait for dn to go low, but I do not adjust the counter based on this. So in order for our counter to decrease, I need to see the entire cycle. I need to see dn go up and then dn go down. That's what we're calling a pulse, right? It goes high and then it goes low. That's called a pulse. I need to see a full pulse before I can decrease my counter. So this high-level state machine is what we call a pulse counter. I set the number of pulses that I want to see at the beginning. That's n. And then when I see a pulse, I decrease my counter. When my counter is 0, I know that I've seen all of the pulses that I was looking for, and so I set my output to be true. Otherwise, my output is false. So the next question is, what does this actually look like in a circuit, for example? So let's take a look at what this particular high-level state machine might look like as a circuit. We have variables now. We have count, right? We have count as a variable. And so we need to have a register that tracks that value. We need to be able to manipulate count. At the very beginning, we set it equal to n, and then we start decreasing the counter. So n is going to come in as an input and be stored in to count, right? So the state machine is going to tell this count register when it should load in that value of n. So this is a load register, like we talked about in the previous section. And then periodically, the state machine is going to decrease count by 1. So you can see here that the state machine will sometimes tell this counter, this register, to decrease by 1. And in exchange, counter is going to tell its state machine when it's equal to 0, so that the state machine can set the output event properly. This state machine itself looks much like the state machine circuits that we've seen already, the state machines that we've worked on in the previous sections of this class. And so what we have here is the state machine acting as a controller of a register. The register represents our important variables. I can have multiple variables if I want to. In this case, we just have one variable that we're tracking. And the state machine is controlling this variable. It's telling it when it can read in values, when it should be assigned to something. It's telling it when it should decrease by 1. And it's asking it to tell the state machine when it's equal to 0 so that it can use that information to set the outputs. So the state machine in this case is not controlling things directly, it's actually controlling this register, and these two in tandem comprise excuse me, the entire high-level state machine. So that's what the circuit looks like. A controller, the state machine is a controller, as well as a register for our variable. Let's take a look at what the VHDL looks like. So we've seen plenty of finite state machines coded up in VHDL. Here's an example of this particular finite state machine coded up in VHDL. Some parts look very familiar. For example, at the very top we see state types defined. Reset, start, previous 0, previous 1. We see a signal for our state, but this line here is important. So here's our variable. Here's our variable called count. We're declaring count as a register, so it is a series of bits. It is a standard logic vector. In this case, we're using 4 bits. We're using 4 particular bits for this variable, which is going to limit, of course, the value that n could be in this particular circuit. So then we start our process, and then because this is a register, it's only going to operate on the rising edge of the clock. So we check for our reset signal and set our reset state accordingly. Otherwise, this should look pretty familiar to you, right? When we're in the reset state, I'm going to read in the value of n and set that to count. That's what we saw on the finite state machine as our action out of the reset state, right? We see our action there out of the reset state. If dn is 0, then I'll move to the previous 0 state. Otherwise, I'm going to move to the start 1 state. That's pretty straightforward. Down here, we see, right, the transitions from start and previous 0 to the next ones. So that's also pretty straightforward. In previous one, we have a little bit of work to do. So if I see that dn goes low again, that's the end of our pulse. I'm going to transition to the previous 0 state, but then I also need to decrease my counter. So here we see an if statement that's going to decrease our counter by 1. We have seen a pulse, so we need to indicate that by decreasing our counter by 1. And then finally, to set the output again in a finite state machine is based on, in a Mealy machine, right, is based on the current state that we are in, as well as the inputs. So we can see in this particular case, our counter is actually driving the output here. So it's not immediately clear, right, that the state and the inputs that the state and the inputs are affecting this output in this particular Mealy machine. But it is in fact true because you can see that count is based on the states as well as the input. Again, remember that the state machine itself is not responsible for this output. This output is kind of separate from the state machine. If you look at the finite state machine diagram, right, that we saw originally, the output's just kind of hanging out down here at the bottom. It's not attached to a particular transition. It's not attached to a particular state. The actions here of this Mealy machine are not affecting the output directly, but the output does depend on count, which is being changed by these actions in this Mealy machine. So the output itself, right, is just kind of independent of everything else that's happening in this Mealy machine. And so then finally, just so we can see how this actually works, a couple of simulations. You, of course, could plug that code, that VHDL code, into Xilinx and simulate this for yourself. I highly encourage you to do so if you have some time and you're able to do that. But just really quickly, here's a couple of simulations. We see at this particular point in time, right, we're going to reset the machine, and as soon as the reset signal is gone, we read in this value of n. So n is here on the second row. In this case, it happens to be 5, so we can see that the counter absorbs that value of 5. The counter is now 5. And so we start traversing through the states. Here's d in. So here's the first pulse. We see as soon as that pulse goes low, that our counter decreases. Here's our second pulse, our third pulse, our fourth pulse, and finally our fifth pulse. After it's finished, our counter is at 0, so our event output, which is on the very bottom row, goes high. This is an example showing the start 1 state. So what happens if d in is already high when we reset the finite state machine? That's not a full pulse as far as we're concerned, right? So here n is 3. We see that 3 gets stored in our counter. d in is already high, so we're going to stick around in the start 1 state until we see d in goes low. That's only half a pulse, so our counter does not change. Our counter has not changed in this particular scenario until we see a full pulse. It goes high and then low, high and then low, and then finally our third pulse indicates our counter goes to 0, and we see the event output go high once again. So what all have we seen here? What all have we learned in this particular video? So if we want to compare the finite state machines to these high-level state machines, the biggest differences we see in terms of the finite state machines themselves. These high-level state machines can have arithmetic. We saw subtraction, but addition, multiplication, whatever. Everything is fair game. Logical operations, so things like greater than, less than, ands, ors. Those are all fair game now as part of our finite state machines, as part of our high-level state machines. They can have variables, so they can use variables to store values. They can actually use those variables as part of transitions, right? They can also have loops. We'll see an example of a loop in the next video. We'll see that next time. I don't have an example of that right now. But those are the big differences between the high-level state machines and the finite state machines that we've already seen. In terms of circuits, a high-level state machine is going to have a register for each variable that it contains. So this particular high-level state machine had one variable. That means there was one register for that particular variable. And the state machine itself is going to be what we call a controller for the register. So the state machine and the registers interact with one another, right, to perform the behaviors defined in the high-level state machines. These state changes in our state machines now can depend on register values. So we can use our variable to decide when to transition from one state to the next. And register values can be changed depending on certain transitions or certain states as well. So I hope you can see that high-level state machines, while they are perhaps a bit more complicated, are going to allow us to perform a lot more complex and interesting things with our finite state machines. This is the primary topic of the last third of the course, so we're going to spend a lot of time talking about these high-level state machines and creating high-level state machines and coding high-level state machines. So next time we will spend some more time talking about loops within our high-level state machines.